Hi, in this video we're going to be looking at the path dependence of line integrals. We've seen that the general form of a line integral is equal to the integral of some curve between 2 points of some function multiplied by ds, and we saw that this can be expressed as the integral of p dx plus q dy. In the first time this was mentioned in one of the previous videos, we said that this p dx q dy kind of looks like the differential, the function differential, where we said dz is equal to p dx plus q dy. And the question we asked at the time was, does this have anything to do with line integrals? It kind of looks, it has the same form, right? So the answer to that question is yes, we can think of the line integral as being an exact differential. So let's just remind ourselves what an exact differential is. If we have some function z being the function of x and y, and then we find the differential of z, and then we see that it's dz dx times dx plus dz dy dy, and we said that p was equal to dz dx and q was equal to dz dy. And we said that if z or dz is an exact differential, then if we differentiate this first derivative with respect to y, it should equal to this other derivative with respect to x, because we know that mixed partials are equal. That is, d squared z with respect to x and then with respect to y should equal to the same thing, but initially with respect to y and after that with respect to x. So if this is true, then our function is an exact differential. So what this means is that the derivative of p with respect to y should equal to the derivative of q with respect to x, mixed partials. So what does this have to do with line integrals? So what it has to do with line integrals is that when we take an integral over a closed boundary, remember when we put the circle in this integral sign, it means it's a closed boundary. When we take the integral of around a closed boundary of an exact differential, the integral of an exact differential, we get 0. Literally, that is exactly what it means. So let's just rewrite this into a way that we understand it. So it means that if we integrate I around a closed boundary of a curve of p dx plus q dy, and p dx plus q dy is an exact differential, then we should get 0. So I think this point is most easily illustrated through an example. So let's just take some function differential. We say 3x squared, perhaps y squared dx. So this is our p, plus 2x cubed y dy, and this is our q. So if this is an exact differential, it means that the derivative of p with respect to y should equal to the derivative of q with respect to x. So let's do that. So p is equal to 3x squared y squared. If we differentiate this with respect to y, then we find that it's equal to just 6x squared y. So if we do the same with q, and then differentiate it with respect to x, that's dq dx. Well, 2 times 2 is 4. Sorry, this is a cubed. Yeah, it's a cubed. Okay, so 3 times 2 is 6, and 3 minus 2 is 2. We get 6x squared y. So what do we see? We see that indeed the derivative of p with respect to y is equal to the derivative of q with respect to x. So this means that it is an exact differential. So if we were to integrate this, if this is our function, and if we integrate it around any closed curve, we should get 0. This is what our assertion is. So that's what we're going to do. We're going to integrate this function, 3x squared, y squared, 2x cubed, y, and let's see if it does in fact give us 0. So we'll take the curve, let's just draw a curve. We'll take two curves. One will be a quadratic curve between 2 points, and one will be a straight line between the same points. So let's, as the curve, we'll choose it to be y is equal to 2x squared. Okay, so let the point be something like a. Okay, then also be the top curve, let it be, for example, 2x. So it's a closed curve that we are evaluating. So our line integral was around the closed curve of this exact differential, and it was 3x squared y squared dx plus 2x cubed y dy. Right, so let's firstly do the two curves. So we have y is equal to 2x squared, that's our bottom curve. So that means that dy here is equal to 4x. And of course, y is equal to 2x, that is our top curve. So dy is equal to 2 dx. So we substitute this into our line integral. So let's write the line integral for both curves. Remember that this is not a single valued function. And in the previous videos, you saw that we had to split it up into two parts. So we have to integrate the line integral from O to A and then from A to O. So let's do that. So the line integral would be from initially, well, A is the point, let's just say 0 to 1. And of course, the y value is 2. So we'll integrate from 0 to 1 along the bottom curve. So that would be 3x squared times y squared, and y squared is 2x squared. So that's 2x squared times dx plus 2x cubed times y dy. Y is 2x squared and dy is 4x. So we have to multiply it by 2x squared and dy, which is 4x dx. And let's not forget that we have to add this to this now. The integral from 1 to 0. Same thing, but now y is equal to 2x. So again, it will be 3x squared times y squared. So it'll be 2x this time, squared, times dx, plus 2x cubed times y, which is 2x, multiplied by dy, which is 2 dx. Simplifying this, 3x squared times 2x squared squared. So x squared squared is x to the power 4. X to the power 4 times x squared is x to the power 6. And 3 times 2 squared, well, 2 squared is 4. 4 times 3 is 12. So we're going to have 12x to the power 6. That's this first term. Let's look at the second term. We have x cubed times x squared. That's x to the power 5 times another x. This is that'll make it x to the power 6. So we have 2x to the power 6's, so we can add them up. So this is the first term was 12x to the power 6, and the second one is 2 times 2 is 4. 4 times 4 is 16. So we have 16x to the power 6 dx. So that's our first integral. And then we add now to this our second integral, second term. So that's from 1 to 0. X squared times x squared is x to the power 4. 2 squared is 4. 4 times 3 is again 12. So we have 12 x to the power 4. And then let's look at the second term. We have x cubed times x, that's x to the power 4. 2 times 2 is 4. 4 times 2 is 8. So we have x to the power 4 as well. So we can just add to this. So that will give us 8x to the power 4 dx. We can just simplify this. So 12 plus 16 is 28. So we have 28x to the power 6 dx. So what we can do is, instead of integrating from 1 to 0, we can just reverse the order of integration. And of course, we have to change the sign when we do that. And 12 plus 8 is 20. So we have 20x to the power 4 dx. So just remember that this first integral corresponds to our bottom curve, that was y is equal to x to the power, y is equal to 2x squared. And the second term corresponds to the top curve, which was y is equal to 2x. Let's just remind ourselves. So that's 2x squared. And that was 2x. So that was the first term, and this is the second term. So if we now integrate these terms, what do we get? X to the power 6, that becomes x to the power 7. 7 times what gives us 28? Well, that's 4. Doing the same with the other term, x to the power 4 becomes x to the power 5. 5 times 4 gives us 20. So evaluating this integral, anything to the power 1 to the power anything is just 1. So we have 4 as the first term and 4 as the second term. What does this give us? 4 minus 4 is 0. So yes, if we integrate this exact differential around this closed curve, it gives us 0, as we had asserted earlier on in this video. So that illustrates the point that if we have an exact differential, and we prove that it's an exact differential by finding day p, day y, and showing that it's equal to day q, day x, and then integrating it, if it's a closed boundary, it will always give 0. So that's the one point. The other point is that if we integrate along this closed boundary, it means that no matter what path I take to get from O to A, I will always get the same value. So let's just explain that once again. It means that if I integrate, I could integrate like that. That's one path I could take. I could integrate maybe another path from here to here. I could also maybe integrate from there to there. There's an infinite number of ways I can get between these 2 points, O and A. Perhaps another path could be the straight line, as we've looked at earlier in this thing. Sorry, let me just use another color there. So regardless of the path that we take from O to A, we'll get the exact same value. Because if we go back along any other path, we'll get the same value, because the integral of the exact differential should be 0. So let's prove that point. I think it'll become evident what I mean if we just look at this example that we have just done. So let's just say we looked at it in reverse. So instead of integrating from O to A and then back along this other curve, the top curve that is, let's just say we integrated from O to A, and then we also integrated from O to A as two separate line integrals. So let's just say I1 is along the path O to A of this function. And let's just say I2 is the integral also from O to A of this other function along y is equal, OA is equal to 2x squared. It's not actually equal to, but we're just using it as an indicator to show what we mean. So let's look at this. We said that the integral along the one curve was 4, right? So this was equal to 4. So it's drawn as an arrow there. So that term corresponds to the integral I1. And we saw that it's equal to 4. And this corresponds to the integral I2. We're going along y is equal to 2x. And that's also equal to 4. So it means that regardless of how we get from O to A, we'll get the same value of the integral. So there's two important points that have come out from this video. And I just want to write those 2 points are, what those 2 points are. So number one, so if p dx plus q dy is an exact differential, then the line integral, so the line integral of the exact differential around a closed curve is equal to 0. So the line integral of an exact differential around a closed curve is equal to 0. That's the first important point of this video. So the second important point is that if this first point is true, then it means that the line integral, so the line integral between 2 points does not depend on the path of integration. The line integral between 2 points does not depend on the path of integration. The path of integration. Yeah. So we have already shown how one is true by using an example. We proved that the function that we're integrating was an exact differential by taking day p, day y, and day q, day x, and showing that it's equal. And once we proved it was an exact differential, we integrated along the two parts. One was 4x squared, was it 2x squared? Well, whatever it was, and along 2x, yeah, it was 2x squared. So we integrated along these two parts, and we showed that it's equal to 0. Then the second thing we did was we showed that the first part, the integral, gave us 4, and also along 2x it was also 4. That means it doesn't matter how we got from O to A, we still had the same value of the integral. So this is a very important point. So that means that for an exact differential, we use the phrase path independent. So that's what it means. So perhaps